Okay, first thing first, thanks everyone for joining us today for another Australian Fluid Mechanics Society seminar series. Our today's speaker is Professor Peter Schmid from Imperial College London. And Peter did his PhD at MIT, and then he moved to Department of Applied Mathematics, University of Washington. And then he moved to somewhere very interesting place in France, French Science Research Agency. And currently he's chair of applied mathematics, mathematics and mathematical physics in the Department of Mathematics of Imperial College London. His research focuses on stability theory, fluid control, model reduction, and computational fluid dynamics. And he is famous to fluid mechanics community mainly because of his 2010 JFM paper on dynamic mood decomposition, which as today, this morning, 2,321 citation, which indicate how important that paper is. With this introduction, I'll hand it over to Peter. Thanks.
All right. Okay, thanks. So thanks the organizers for the invitation. So I'm not going to talk about DMD today. I thought I would talk about mixing enhancement in binary fluids using an adjoint-based optimization scheme. And this is the thesis work of Maximilian Egel, used to be a postdoc at Princeton, and as of yesterday is at the Max Planck Institute for Brain Research. So let me just start out with a definition of mixing, because it's very important to understand what we actually mean by mixing. If you look up Wikipedia, you get the following definition. It's making a heterogeneous physical system homogeneous using manipulating operations. So we're starting out with something that is heterogeneous in its composition, and then we want to somehow bring it into a more homogeneous state by manipulating operations. So we're going to be a little bit more specific about that one as we go along, but this is a pretty good definition for the layman. So I don't think I have to convince you much that mixing is very important in a variety of physical technological processes. The food and beverage industry is doing a lot of mixing. Of course, pharmaceutical industries, when they mix the medication, is using mixing all the time. They probably have one of the highest tolerance standards in the mixing industry, but then also consumer product industry, adhesives, sealants, cosmetic, shampoos, color, paint, things like that, all involve mixing at one point or another. Civil and chemical engineering, same thing, wastewater management, polymer production. Every time you have a chemical reaction, it gives a better product if it's well mixed ahead of time. Oil and gas industry, of course, the refining technology, biofuels, pulp and paper industry. But then there's also a big section of mixing that is not industrial or not technological, and that one is natural mixing in oceanography and the atmospheric sciences, nutrient transport, and then natural and man-made disasters. Oil spills, for example, come to mind there. Of course, in the latter ones, we don't have much way of doing the manipulating operations according to the Wikipedia definition. All right, let me just give you the setup of the kind of mixing we're interested in. Of course, we're going to boil it down to something that is a little bit more manageable. We want to have a maximum mixing with the least energy expenditure. Okay, so that's the wish list. We have to turn that into an optimization problem with constraints. So we're gonna at the end solve a constrained optimization problem. That's where the adjoint-based techniques come in from the title. We're gonna have the constraints, of course, with the governing equation, but also we want to constrain the time horizon. We don't want to mix forever. At some point, we're gonna stop the mixing action and then trying to get as best a homogeneous mixture as we can. And of course, we also want to limit the expended energy. So in one word, we want to have minimal effort but maximum outcome. Now, there's a physical intuition that has been around for a long time. Whenever you say minimal effort with maximum outcome, you immediately think about an instability. So if you have a hydrodynamic system that has an instability, an exponential linear instability, then this would qualify as minimum effort for maximum outcome. So because if you could piggyback on a instability, you would actually use a infinitesimal effort, an epsilon effort, and then let the instability do its amplification and then get a maximum output. So we're going to look into this one and see whether we can actually exploit these instabilities and get some of this growth from the intrinsic growth of an infinitesimal driving or an infinitesimal initial condition. Okay. So let me try a first attempt here. That one is a very simple setup. We have two-dimensional Poiseuille flow. So flow in a channel, parallel walls. And we flow through with a parabolic profile. Then we have a fluid that is labeled as 1 and 0. So it's a binary fluid. The bottom is theta, the passive scalar is equal to 1. In the top, it's 0. So I indicated that with blue and white. And then we allow blowing and suction at the wall. Okay, and independent, the top wall can blow differently than the bottom wall. Excuse me. And anything is allowed. We have a finite time horizon and we have a finite energy. Okay, and the job is to mix up this blue and white fluid into a well homogenized, well mixed fluid. Okay, so we're going to consider two cases here. The first one is we're trying to optimally force the flow instability. So that goes back what I said on the previous slide. We're trying to use the intrinsic instabilities in the fluid system to get the mixing done. And the second case is we're gonna address mixing directly. We don't care about an instability. We just want to have the end result to be a well-mixed binary fluid. Okay, I'm going to explain what we actually target later on. I just want to somehow eliminate case number 1 as a viable option. Okay, and like I said, impose constraints, limited control time strategy, and limited control energy input. So here are some the figures. I'm going to show you first what happens if you have if you do it with the instability. So let me just explain these four panels. The most important one is in the bottom, of course. This is the passive scalar. We have blue on the bottom and white and on the top as our initial condition. So we will see as the movie starts that this will change and will stir up. The second one from the bottom is the velocity field that we actually instigate. And I subtracted out the profile, the mean flow profile. Okay, and then the top two is what kind of forcing the optimization came up with, and that one is the top one is the upper wall, and the second one is the lower wall forcing. Okay, and that one is an XT diagram. So T goes from 0 to 50, and X goes from 0 to 2 pi. Okay, so we see that the upper wall forcing and the lower wall forcing in the XT diagram, it looks like as if there is a wave going down, okay, over 20 time units. Then after 20 time units, that's our time horizon, nothing is allowed anymore. Okay, we're done with the mixing. After that one, the flow will of course have rest inertia and move on, but we're not doing anything actively at the wall. So let's see how well we're doing with a fluid instability. Okay, so here you see the blowing and suction on the wall. We're going to squeeze down like a peristaltic wave in a sense. Okay, half the time horizon is already gone. We see that we're stirring up the flow. Okay, now hands off. Nothing is allowed anymore. There's no control anymore from the walls. The flow evolves just by rest inertia and diffusion, basically. Okay, so you see that after we're done with the mixing, as much as you can call that mixing, the bottom is still blue and the top is still white. So we haven't really done so well using an instability in the flow. So let's now target mixing directly. Okay, and I will say what that is on the next slides. We're going to work through that one. The thing to recognize here is if you look at the top, the mixing strategy, it's more or less the same, right? So it's this wave motion that goes down the channel, a little bit like a traveling wave. So in the XT diagram, we have these red bands and these blue bands that indicate blowing and suction as we go down the channel. Okay, so let's see how well we're doing here. Okay, starts out almost the same. We blow and suck from the wall. We stir things up. But now something very different happens in the passive scalar. We're actually producing filaments, very thin filaments. So we use the shear of the flow very, very differently. Now it's 20, no mixing anymore. And from there on, now we just diffuse. But at time is equal to 20, we produce so many small scales and so many small filaments that diffusion will now do the rest. Okay, so there's a big difference between those two things. One is using an instability, and one is using mixing directly. So I think you all agree that we can actually discard this strategy of using an instability only and targeting that as the part that is doing the mixing. So hydrodynamic instabilities are inefficient mixers. And the instabilities usually concentrate on the large scales. You saw these big rollers. They don't produce enough small scales that the diffusion could then kick in and mix to the end. Okay. So mixing has to generate flow filaments by using the shear in a very smart way. So the active mixing part is almost like a preconditioner. It preconditions the flow into small scales and small filaments. It transports it down towards smaller scales so that to prepare it for mixing by diffusion. Okay, so we're gonna exploit this one in a adjoint-based optimization. And the way we're gonna do that is by mixing by geometry. We're not doing blowing and suction on the wall. We're actually mixing by geometry, okay, by stirrers. All right, the physical model, very simple. We have a binary fluid, so only two components, and we're going to assume it's Newtonian. We're thinking about going non-Newtonian at some point, because that entire list I gave you in the beginning about consumer products and food products, they certainly are non-Newtonian. But we're going to stick with Newtonian just for simplicity. We also have an incompressible flow, and we're going to go with a two-dimensional flow at a Reynolds number of 1000. The choice of Reynolds number of 1000 is very deliberate because we want to be in a regime that is beyond the Stokes mixing. There's a huge literature about Stokes mixing at very low Reynolds numbers. There's no inertia at all. It's a very special kind of mixing. But at the same time, if you go for the Reynolds number too high, then you have turbulent mixing, and then all hell breaks loose, basically. And the adjoint-based optimization is losing its efficiency in a sense. I'm going to say a little bit more about that later. So the Reynolds number of 1000 puts us exactly in between that Stokes regime. We have to care about inertial effects, but the Reynolds number is not big enough for turbulent effects to come in. We also use a cylindrical vessel with two cylindrical stirrers on circular paths. That's our setup, and that one is in response to an experiment that we can compare to. Okay, so this is how it looks like. We have a little bit like a Petri dish. Think of it as our mixing vessel. We have two cylinders, two rods going around on circular paths. And in the beginning, we have the lower part, theta is equal to 1 for the passive scalar, and the top part, theta is equal to 0. Okay, just like in the channel flow. All right, so the mathematical model, Navier-Stokes equations, two-dimensional, incompressible, very simple. And then we have to augment that with an advection diffusion equation for the passive scalar for describing the blue and the white fluid. So theta is equal to 1 is blue, and theta is equal to 0 is white. And then in the end, what we wish is a theta of about just around 1/2 everywhere. That would be perfectly mixed. We also have to decide on the Peckley number. The Peckley number is 1000. That gives us a ratio of Reynolds to Peckley number of 1. So we're thinking a little bit more in the regime of a mixing of a gas than of a fluid, but we're also exploring other regimes where the fluid is more liquid-like rather than gas-like. We have no slip boundary conditions for the velocity on the moving static geometry. And we have a no penetration boundary condition for the passive scalar. Okay, so Dirichlet, Neumann, Dirichlet for U and Neumann for theta. All right, the computational model is a masking model. So this one is known under Brinkmann embedding or Brinkmann penalization. So we embed the moving boundary conditions in a uniform Cartesian grid. So we have a Cartesian background grid, and the stirrers move through that grid a little bit like an immersed boundary. But we do a penalization technique, which is very much related or almost the same. We have geometric masks for representing the stirrers and the computational domain. So we have chi of I. Each stirrer gets a mask that is 1 if we're inside the stirrer and 0 otherwise. So this is how we decide on whether we have a grid point that behaves like a solid or a fluid. Okay. And if you bring all of that in, the masking in, you have to augment your boundary condition, your governing equations, and you get additional terms, just like with the immersed boundary method, that penalize the velocity to bring it down to the stirrer's velocity. So if you see the box, if you see this box here in the U equation, this one is the difference between chi and chi I, and that one basically brings the fluid velocity to the stirrer velocity once we're close or inside the stirrer. We have to do the same thing. We have to augment the theta direction for the Neumann boundary conditions. That one is a little bit more complicated because now the mask also shows up in the diffusion term. Okay, this is how you enforce 0 gradient conditions on the stirrers. Okay, so now we have 2 control variables. By introducing our geometry, we have 2 control variables. First of all, the chi I describe the stirrer geometry. So we can actually do shape optimization if you think of the chi I for each stirrer. So we have chi 1 and chi 2 for our 2 stirrers. If you have more stirrers, you have more chis. You can actually change this variable and use that one as a control variable for the optimization. In that case, you do shape optimization. Or you can freeze the shape and say, okay, my stirrers will always be circular in cross-section, but you can control the stirrer velocity on the circular paths. Okay, this is what we do first, and then I show you in a second example how to do the shape optimization. Okay, so and then of course you can bind the 2. You let both loose and say I want to have the velocity and the shape optimized at the same time. Okay, so that one just increases the number of control variables. That's all it does, but the framework goes through the same way. Okay, few implementation details. We did not start writing a code from scratch. We actually used a open source code called Fluzy, written by Kai Schneider for fluid structure interactions. But we really stripped this one down to the bare bones and just use it for the hydrodynamic part. It's a spectral Fourier-based discretization on a doubly periodic domain that is actually blocked, so you can embed any boundary conditions you want. You have a pseudospectral treatment of the nonlinear terms. We use the aliasing because we're always pushing the boundary of the resolution. We do that by a Lee-Howe filter. We have a grid mass transfer, so the way to transfer variables that are on the geometry to the background grid by a modified delta function. And the code is also highly parallelized using an FFTW library with P3D FFT. Okay, so it works on parallel machines quite nicely. And for these type of optimizations, you need parallelization. This is not something that you can run on your laptop anymore. Okay, so what is the objective? We want to enhance mixedness within a given time horizon using a finite control energy budget. Okay, I'll say a little bit more about that later. Instabilities cannot be exploited. They're certainly part of the mixing process, but should not be targeted as a proxy for the control strategy. So now we have to face up to defining what we actually mean by mixing. What is a good measure of mixedness that our optimization strategy could target as the variable to optimize? And it actually turns out this is a very active research field, and the mathematical definition of mixedness is more complicated than you might expect. Okay, so there is usually two options for that one. Number one is the variance, and that one is a perfectly good mixing measure. So the variance is the norm of theta minus its mean. So it's the variation of the scalar product. The more homogeneous it is, the lower the variance. Obviously, a very nicely mixed homogeneous scalar product would have a variance of 0. The definition is based on the fluctuations from the mean, and perfect mixing, uniform mixing, would mean a very, very low variance or even a 0 variance. Now, the nice part about that one is, the advantage of that one is, you see the squares there, the norm squared and the mean squared. So this one is an L2 measure, and optimization just loves L2 measures because it's a nice and convex part of the cost functional. Okay, so in that case, we will have a very well-behaved optimization based on the cost functional itself. The governing equation actually throws a monkey wrench into the whole thing, as I will explain later. Okay, but there is also a problem with the variance. It's not only everything is good with a variance, there's also a problem. And if you write down the evolution equation for the variance, you actually see that advection is explicitly absent in the evolution equation. So it only has the diffusive part, but not the advective part. But we've seen from the example with the channel flow that advection is enormously important in getting these small filaments going. And if that one is absent in the variance, this is some kind of a drawback of the variance as a measure for mixing. Of course, advection is implicitly there because it's the part that causes the gradient. So in the gradient of theta in that equation, the advection has produced these gradients, but it's not explicitly there. Also, if you have low diffusivity and effective stirring, which is exactly what we have in our case, the Reynolds number of 1,000 is quite high there. The variance is an unsatisfactory measure because it doesn't give us much of a gradient to work with to improve. There's the second option that we're choosing, and that one is a specific norm that is made for mixing. It's the mix norm. So that one is particularly designed for mixing problems. And if you write it down, it's the nabla to the minus q of theta and the norm of that. And q, the power here, is between 0 and 1. So it's not even does not have to be an integer power. You can pick -1, and many people do, but we're actually doing all our simulations with 2/3. Okay, so you have a negative 2/3 gradient of theta. Okay, so first we have to define what does that mean. Okay, this is what's known as a negative index Sobolev norm, and the gradient to a fractional power is what's called a pseudo-differential operation. So it's a fractional derivative. And because it's negative, it's not really a derivative. It actually, you can think of that as a fractional integral. Okay. A 2/3 gradient would be a 2/3 derivative, and -2/3 gradient is a 2/3 integral. Okay. So it's an integral quantity, that's why negative. So the operator smoothes out a passive scalar. Derivatives always make whatever you take the derivative of rougher and rougher, more and more jagged, whereas integration makes a function that you integrate smoother and smoother. So we're going into the smoothing part. That's already good. And it also acts like a filter because the small scale variations are not detected by using this norm. Okay, so you can interpret this one best and get a little bit of an intuitive handle on that funny norm by going into Fourier space, because then let's say we have the nabla to the -1. The gradient turns into a multiplication by ik, the wave number, to the -1. Okay, and that one, the ik to the -1, you can think of that one as like acting like a filter. Okay, so the higher the k, the less important this is. Okay, so you can also define that mixed norm without going to Fourier modes. In that case, you have to do a little bit of extra work. I'm writing the ik to the -1 as minus ik over k squared. So in that case, the 1 over k squared would be the solution to a Poisson problem. And then the ik would be a differentiation of the solution of the Poisson problem. So you can actually transfer that one to non-periodic and non-Fourier transformable passive scalars as well. Okay, so in our case, like I said, we're going somewhere in the middle of this interval. In our case, we use q is equal to 2/3. And that one, you can actually argue for that one. It's very mathematical. You need ergodic theory and optimal transport for that. All right, that's all I want to say about the way we measure it. So we have to also have constraints. We wish to enhance the mixingness given time horizon and so on. Okay, so the mixed norm only involves the dynamic variables. Okay, only theta goes into the mixed norm. U is not really there, but we have a governing equation for U. Every time you have an optimization or a control problem where what you control is not involving everything that you have a governing equation for, you actually have what's called a semi-norm problem. So that means you have a hidden variable, in our case it's U, that can be as high as it wants to be because it's never penalized. It never shows up in the control, in the cost functional that we wish to optimize. Okay, so in that case, you get ill-conditioned optimization problems where one variable is just running away from you because it doesn't show up in the way how you measure success. Okay, so we need to limit the hydrodynamic energy in U in different ways. And to do that one, we have to have extra constraints that I'm going to go through once we get through the examples. Okay. All right, so we have an optimization process. We have our objective. We identified how we want to measure that one. It's our mixed norm of the scalar product. We want to drive that one to a minimum, but we also have constraints. And the constraints come in two varieties. One is we have to satisfy the governing equation, of course, the Navier-Stokes equations and the passive scalar equation. And then we also have to put on top of that the constraints that are dictated to us by having a semi-norm problem, by not considering the velocity in our mixed norm. Okay. So once we have all that identified, we can turn a constrained optimization problem, standard way of doing that one, into an unconstrained optimization problem by adding the constraints to the objective to make the objective function augmented or bigger. And we do that one by multiplying with Lagrange multiplier. So L mult is the Lagrange multiplier. We have each one for each constraint. So the governing equations, the U gets a Lagrange multiplier, the theta gets a Lagrange multiplier, and anything else we want to enforce gets its own Lagrange multiplier. Okay, so everything is lumped together in one big cost functional. And then we're going to minimize this one altogether with respect to all variables that are considered. So we have to take the first variation of this augmented Lagrangian, and we have, from that one, we get our governing equation. So this one line that is there, L, dl, d0, delta L0, the first variation of L is equal to 0. Out of that one, we can squeeze out 3 governing equations. The first one is the governing equations that we already have, so that one gets reproduced. The second governing equation that we get is a governing equation for the Lagrange multiplier. That's the adjoint problem. And then if we take the variation with respect to all the control variables, whatever we decide on controlling with, we get an optimality condition. Okay. So once we have all these 3 equations, we have to solve them simultaneously, but nobody does that one. It's a very complicated system of equations. We actually solve that one iteratively. So we get the first governing equations. That's the one we already had in the beginning. Okay, that's the hydrodynamics and the tracer, the passive scalar. That's the nonlinear Navier-Stokes equations for each one. We solve that one forward in time over our time horizon from 0 to capital T. Okay. The second equation that we get out of this optimization problem is the adjoint equation. That one is governing the Lagrange multipliers, which are sensitivities. So we get one equation for the hydrodynamic sensitivity and one for the tracer sensitivity. Now, these 2 equations on the bottom are actually linear. The top one is nonlinear. That's the nonlinear Navier-Stokes equations. The bottom one is linear, but has a driving term that comes from our cost functional. And here is our cost functional, the nabla to the -2/3 theta d omega. So it's driven by a fractional derivative. Okay? That makes that set of equations what's called a pseudo-differential equation. It has integer derivatives, the ones we're usually used to, and it also has a fractional derivative from the driving term. These equations have to be solved backward in time. You can only solve them backward in time from capital T to 0. And what you get along this integration is a gradient of what you want to accomplish versus the control parameter. In our case, it's the velocities. Okay, so this one comes out of that bottom equation, and then we use that outcome to stick that gradient di dus into our favorite optimization scheme, slap on any more constraints that we have not satisfied yet, and then use that optimization scheme to give us a better mixing strategy. Okay, so this now is an iterative loop. The first time in the mixing strategy, we guess our velocities of the stirrers. Then we go through one cycle, and next time the mixing strategy hopefully is doing a better job in minimizing our mix norm than it did before. I should also mention, the lower the mix norm, the better we are mixed. Okay. So there's one more hiccup to the whole thing that is causing quite a bit of headache, and that is, as you solve the sensitivity equations on the bottom backward in time, you actually need the solution of the forward problem. So that means if you want to solve the backward equation, we have to save all the flow fields and passive scalar fields of the forward integration, because we need it as variable coefficients in the backward equation. Okay? That makes the whole thing tightly coupled between the forward and the backward problem. They're not independent of each other. And to do that, we have to do what's known as checkpointing in the business. Okay, so before we actually see whether the whole thing works, let's just do a little bit of a thought experiment and say, if you were in charge of mixing, and here is our setup, our little petri dish, blue in the bottom, white in the top. We have circular paths. I give you 2 stirrers, and I let you do whatever you want to with any velocity you want by doing these 2 stirrers. So you can design a control protocol, a control strategy for these stirrers any way you want to along these circular paths. You can go back and forth. You can, spin around like mad. You can do whatever you want to, but you only have a finite time horizon and a finite energy budget to spend. What would you do? What would be a possible mixing strategy? The first thing that comes to mind is a strategy that we label plunging. Of course, you want to get as quickly as possible the stirrers to the interface and then plunge through it to mix it up, right? That's sort of strategy number 1. But that's not the only one. Okay. For example, strategy number 2 would be what we label as the vortex cannon. Remember that the 2 stirrers are actually in the fluid. So if I jiggle them around back and forth, I actually create shedding vortices, starting and stopping vortices by just going back and forth in a jerky motion. And then these shedded vortices, if I do it right, would sooner or later move to the interface, and then the vortex would wrap up the interface rather than the cylinder by itself. Okay, so this is almost like a long-range strategy where the stirrer not necessarily has to be at the interface, but still can reach the interface by shooting vortices towards it. Okay, that's a possible strategy. Okay, another one is obstruction. Once I have seeded a lot of vortices in my flow field, I can actually put the stirrer in the path of a vortex and have that vortex split on it. So that would be the obstruction strategy. That's another one. We'll actually see all of them in a second. And then the other one is if I'm really good at creating these vortices by the vortex cannon strategy or by the wake of the vortex of the stirrer plunging through the interface, I can actually manage to have them collide into themselves, create more shear, and distort whatever passive scalar is in their neighborhood. Okay, so these are more or less the 4 strategies. There's also another one that is wall collision, but it's sort of a sub-strategy of number 4. All right, just a little bit of a setup about the optimization. I'm going to show you movies that last for 32 time units. Okay, that's just a movie. That's the movie time scale. Has nothing to do. I could have shown you 25 or 40 time units or something. 32. Okay. The optimization in all cases that I show you goes over 8 time units. Okay. So we're going to solve the forward problem and the adjoint problem over 8 time units. So the flow knows, the optimization knows exactly what goes on in the flow over 8 units. But then I'm giving you 2 control strategy. One is a very short horizon strategy, and the other one is a long horizon strategy. In the short horizon strategy, I give you 1 time unit. So you only have time to control for t is equal to 1. After that, the stirrers will stay wherever they are at t is equal to 1 and not move anymore. But the optimization will still have seen everything up to time horizon 8. So it will know what happens after the stirrers stop. Okay, that information is part of what you do within the time unit of 1. In the time is equal to 8, we're going to use the stirrers as much as we have information for them. Okay, and that one is more of a slower strategy. You have more time. You can be a little bit more deliberate. If you have less time, t is equal to 1, you have to get the job done, because after t is equal to 1, nothing will happen anymore. You can blow your entire energy budget over 1 time unit. Okay, so you get higher speeds. But from 1 to 8, there is nothing else you can do anymore, even though you know what will happen next. All right, so let's do first results. we're going to start slowly. We actually only take one cylinder in the beginning. And we're going to penalize our energy. So we say we can only use a certain amount of energy. Time is equal to 1. So very short mixing strategy. Okay. And then we throw the entire thing at the optimizer. And I should mention that the time and the budget, the energy budget and the time horizon is enough for that stirrer to reach the interface and do some damage and plunge through the interface. Okay, so there's enough time there. But nevertheless, by optimizing this one, this is what happens. This is what the optimizer, the adjoint optimizer, decides to be the perfect strategy. Okay. So it doesn't go through the interface. It could reach the interface, but rather than going through the interface, what it does is, I'm playing that one again, it jiggles back and forth, creates a lot of shed vortices that sooner or later, even after the control strategy is done, still can stir the fluid. Okay? And only after that, after these vortices have been generated, does the stirrer move towards the interface, stop there at t is equal to 1, let the stop vortices overtake the cylinder, and then distort the interface. Okay, so the first thing that you see distorting the interface is the stop vortex at t is equal to 1, and then only then do the other vortices that it generated by jiggling back and forth also distort the interface. Okay, so it's actually a quite smart strategy, because, as I said, the integration is over t is equal to 8. So the optimizer knows what will happen from t is equal to 0 to t is equal to 8. It also knows that it only has t is equal to 1 as a unit. So it optimizes what it can do from 1 to 8 by generating vortices from 0 to 1, that later on, when the stirrer cannot do anything anymore, it just sits there, it still has spawned enough vortices that do the stirring or continue to do the mixing after the stirrer is done with its job. Okay, and that one is actually quite nice. First time we saw that one, no, I would have bet money on having that stirrer plunge through the interface. And when we first saw the results, it was almost like a little creepy that the adjoint optimization actually figured that thing out with a vortex cannon. Okay, very smart. Now we also did. I don't have a movie with in the presentation here. You may say, okay, that one was a little bit forced because we started the stirrer so high up. And I told you, yes, it has time enough to plunge through the interface, but we wanted to make it more extreme, and we set the initial position of that stirrer right on the interface. So it was already there, halfway embedded already in the interface, and we were sure now it's going to plunge through. And it still did not plunge through. Even if you place this one as an initial condition on the interface, it will still do that jiggly dance and create all these vortices before it actually plunges a little bit. Okay, here is another visualization. So you see the jiggling, and then now we trace the biggest vortices. So you see the trace of the vortices as they spiral around and do the mixing. Okay, quite a nice dance of these vortices. Okay, now the problem with this one is it's not constrained enough. Okay, I say here this is energy penalization, but like I said, the energy penalization is not enough. It's a semi-norm problem, and if you optimize more and more, the jerky motion will get more and more jerky. There is no upper limit because you just spend the energy that I give you in a shorter and more accelerated fashion. So you can generate shed vortices almost to any degree and any vorticity that you want. Okay, so this one is an open-ended optimization. It never finds really the optimum. It makes it better and better and more mixed, but there is no limit to it. This is an unconstrained problem. It's like one of those optimization problems that runs away from you. So we have to constrain that a little bit more. But I actually jumped ahead here. Sorry. Let me show you what happens when you do two. Okay, two stirrers on that circular path. So now we have a little bit more possibilities, because now both can do this jerky motion, and they can actually shoot vortices towards themselves. Okay. So now they can actually play with each other and go into this pinball activity with the stopping and starting vortices. Okay. And that's exactly what we see here. I'm going to go back. It's going to play in a second. You see also there is a jerky motion in the beginning. The vortices shoot through the interface and stir it up. We have a collision here that is in the obstruction category. You see that plenty of these vortices are actually bashing into each other or into the wall. Okay, so it's quite complicated, but more or less it follows the same strategy. The stirrers don't go through the interface, they shoot from far. Okay. But as I said, this is a diverging optimization. There is no upper bound to it. We have to restrict it some more. And now if you actually think about it, the energy penalization is not enough. A velocity penalization is not enough either, because the shed vortices, the strength of the shed vortices for starting and stopping are actually proportional to the acceleration. Okay? The more we accelerate, the more we get vorticity pumped into our mixing strategy. Okay? So what we actually have to constrain is an acceleration of the stirrers. We have to go one derivative higher than the velocity bounds. We have to actually have acceleration bounds on the stirrers. Only in that case is the semi-norm problem turning into a proper norm problem where the optimization converges. Okay, so this is the acceleration penalization. Same thing. T is equal to 1. Actually, let me stop that one for a second. T is equal to 1, so we have a very short time horizon. We're going to penalize with, obviously, the governing equations. We also have a finite time horizon, T is equal to 1. We have a finite energy budget that we can spend over T is equal to 1. We cannot exceed that one. But then we also have to make the whole thing convergent, we have to make the acceleration of the stirrers to be limited. Okay, we cannot exceed a certain acceleration of the stirrers. And with that one, we actually converge to a feasible control strategy. So what does actually happen? So let me go back. So you will see that these guys, again, it's now a mixed strategy that uses all 4 strategies. So you will see actually plunging. Plunging is now a viable option. The vortex cannon still is dominating in the beginning. And then we also have obstruction and collision. Okay? So if you look at this one, okay, you actually, if you look closer, here was a nice vortex collision. You actually see very nice stirring. Okay. If you go for a longer time horizon, this is what happens. Much slower. Okay, you have more time to spend the same energy, but very interesting behavior now. you actually plunge through, but as you see, you plunge through, but you also have a jerky motion as you plunge through. I'm going to play that one again right from the beginning. Let me stop that one and go back. Okay. And actually, let me manually, just as you approach this one, okay, you will see just about now, when I run the movie, you will see that the cylinders will stop. Then shed vortices, the wake vortices of the cylinder will basically take over and overtake it and go through the interface before this one plunges through. Okay. Then it will go pretty much on a path around here and then stop here and then shoot the last stopping vortices through the interface on this side. Okay, so I'm going to run the movie. Stop, go, stop, go, stop, and go, and stop, and go, and stop, and go. This is not a, it's not the movie. The movie is playing continuously. This one is actually really a stop and go movie. Okay. So this is a way of using everything that is in the arsenal given by the Navier-Stokes equations to generate vortices on proper paths and making them collide into the wall and splitting up to make smaller and smaller scales and more filaments until diffusion kicks in. Okay. Here is the stop and go. You also see that one here. If I rewind that one, you will see that there's a stop and go vortex here too. So here's the vortex. So if you watch this guy coming up and then stopping, oops, sorry, I messed that one up. I let it go. Okay. So you see plenty of these smaller vortices being shed, and now when it stops, you see the overtake. See all these small vortices, and they all do their job in the interface, mixing them up, colliding into other vortices, being deflected, and so on. It's a real pinball machine. Okay, so let me move on a little bit. This is just sort of the different strategies. We get very good mixing. We get all kind of a complicated interplay of all the strategies that are available for the optimization, and it's really, to us, it's very mind-boggling that the adjoint optimization, the nonlinear adjoint optimization, actually finds all these ways and these complicated interplays and uses them to get the job done that we ask of it. Okay, so I want to just quickly go through the same thing again, but now the only thing that changes is that gradient down there, because now we're going to do shape optimization. So we're not optimizing what the stirrers can do on that circular path. We leave them in the middle, just let them turn, but we say, what is a better stirrer shape? Okay, so we have cylinders, and we say, is there a better cross section that does a better job for a rotating stirrer? Same optimization problem, but now we're optimizing with respect to the mask rather than the velocity along the paths. Okay, so this is the setup. Here is the unoptimized one, and we don't start with a cylinder because a cylinder has nowhere to go. So finding a gradient of what to change the shape on a cylinder is it's hopeless. So we have to give it some kind of a starting strategy that creates some type of mixing, and for that one we have an asteroid. Okay, it's an epicycloid, a hypocycloid. Okay, so this is the starting. This is unoptimized. This is our initial shape, and we're going to go for one full rotation. Okay, it stirs a little bit in its neighborhood. One full rotation once around, and this is what you get. And now we say, what kind of shape would do a better job over one rotation and get the whole thing stirred up a little bit better? And this is the shape that we have. Okay, it looks a little bit awkward. This is a Fourier transformed shape, or a parametric description of a shape with 16 Fourier coefficients. And if you let that one stir, again, we do the mixed norm optimization. This is what you get. Okay, so it's more of a paddle, but it still has these tiny cavities. So there is a small cavity here that sheds very differently, and there's actually a vortex in here that at some point in the rotation shoots out and interacts with the vortex that is shed off from the end, from the long side of the paddle. Let me do that one again. Okay, so here's the vortex being generated and shot out. Okay, so again, over one optimization, this is doing a much better job. If you look at the end picture from the left and the right, this is doing a much better job in terms of the mix norm. Of course, we have way to go to really mix that one properly, but it does a much better job over that finite time horizon with an improved shape. The shape optimization is a little harder to do than the velocity optimization because you also have to worry about little pieces breaking off when the shape curve self-intersects. So there has to be all kind of regularization and things you don't want to do. Okay. So as a final example, we have 5 stirrers here. They all turn. So here's the initial condition. This is how they turn. Okay. And we deliberately placed a stirrer here into the red fluid and here into the blue fluid. They don't do anything because they're in a homogeneous mixture in their neighborhood. Okay. So if you were an optimizer and you would have one rotation, you probably would not do anything on this ones because you should not waste your energy on this one because this one over the time horizon that the optimizer sees does not really see any mixing opportunities whatsoever. So if you do the optimization on this one, then these are the shapes that you get. You see that this shape here and this shape here is more or less untouched because they don't participate over the time horizon in the mixing. And then you also get very nice curves here. Once I play the movie, they act like a gear. So where they have a perfect 90-degree phase in most of the lower Fourier coefficients so that they interact like a gear system. And we did not impose that. This is what the optimizer finds by itself. Oops, I went the wrong way. So let me stir that one up and stir that one up simultaneously, and then you see the difference. So there's a lot more squishing there. It's the same area. It's area preserving, by the way. So the cross-sectional area of the stirrers is a constraint. It can deform it, but it cannot make it bigger. There is only a finite amount of that. Okay. All right. So nice interacting gears that increase the stirring. All right. So I'm coming to the end. What are the remaining challenges and the next steps? Well, the big elephant in the room here is we only can find local optima. This is a gradient-based optimization of a non-convex problem. So in that case, we cannot really find a global optimum. We can only find a local optimum. But I just want to remind you that mixing is a really important concept. And even if you make a small improvement, even if finding a local optimum, a better local optimum, could translate into enormous savings in the mixing industry. Also, we have to do additional constraint handling. The length of the optimization window is also a little bit of a problem because we chose t is equal to 8 as our optimization window. If we go longer and longer and longer, the flow becomes so complicated that the adjoint optimization integrating backwards does not bring back any gradient that can be used in an optimization scheme. Okay? So suddenly it becomes so sensitive that the real sensitivity that we want to exploit is swamped by the complexity of the flow itself. This is a phenomenon you often have when you do chaotic systems or turbulent systems. And that's why we wanted to stay away from turbulence, because the adjoint would somehow not bring back any usable gradient information. We want to go to a higher Reynolds number. The simulations that Max is running right now are at the Reynolds number of 10,000 and a Peckley number of 100. So we're getting closer into the liquid regime. And we also want to look a little bit into the robustness of the stirring strategies. We've played around with making changes here and there, and we saw that even those small details may change about how the vortices go into each other and bang into each other. But the overall strategy of using that vortex cannon or collisions with the wall or this jerky motion of the stirrers, that one was robust over a wide range of parameters. Okay, we want to go towards non-Newtonian fluids, a simultaneous shape and path optimization. We've done that by now. And the results are very preliminary, but look very, very good. We can also optimize, of course, the wall. We can have wall corrugations. Wherever we see that a big vortex runs into a wall, we can make a little bit of a fence there to split it nicer. We can also do injection mixing, where we have a source and a sink. So we pump in something that is not mixed, and we suck it out on the other side, hopefully in a mixed way. And we can also design passive mixing by pressing unmixed binary fluid through a kind of a baffle system that does the mixing for us, and then design that baffle system in an optimal way. All right, so with this one, I just leave the conclusion sides up. Here is one more vortex cannon simulation that stirs up the interface quite nicely. And I'm happy to take any questions. Thanks a lot.
Thanks, Peter, on behalf of everyone. I think we have a couple of questions in the chat box. If people like, they can unmute themselves and ask those questions. I guess first person is Guy. Do you like to unmute yourself and ask a question?
No, it's always hard to find the unmute button. As I was wondering, in the first set of optimizations, if the as it's iterating through, is it essentially maximizing the number of vortices that is generated?
Yeah, without the acceleration constraints, it's maximizing the vortices that it generates. Absolutely.
Okay.
But then there is no upper limit, because the higher you accelerate within your energy constraints, the more vortices you get. And that's why the optimization is running away from you. And when you put the acceleration as an additional constraints into the optimization, that's when you only generate a certain amount of vortices.
Ah, all right. Thank you.
Mm-hmm.
Sean, do you want to ask your question, or is it just a comment?
Hi, Sharm. No, I actually have a question. Hi, Peter.
Hi, Sean.
It was a really interesting talk. Thank you very much. I had a question, two questions. One's very simple, I guess. What exactly is a filament? Is that like a how do we define a filament? I wasn't quite sure what you meant by that.
Well, a filament is a long stretched sheet of vorticity, basically. Okay. So it has to be. I'm not sure whether there is a technical definition of a filament, but it certainly has to have one small scale in one coordinate direction.
Okay.
So usually filaments have one long scale and one short scale. So think of it as something that is like a stick. So it's long in one direction and it's very short in the other direction, in the transverse direction.
Thanks. Then my other question was about the initial condition for the mixing strategy. So does that initial condition need to be prescribed for the time horizon that you're looking at? Or
no, the initial condition for the stirrers is a uniform velocity on the circular path.
Okay.
So we just have a certain velocity, for example, a velocity is equal to 1, that it holds over one time unit, and then it stops. So a hat function basically.
And is that the initial condition for all the simulations?
For the optimization, yeah.
Okay.
And then in the next iteration, for example, if it wants to go back and forth, then that hat function that is just one and uniform moving down towards the interface is now a very short sine function. So it goes back and forth and comes back.
Okay, thank you.
Mm-hmm.
And we have another question from Esteban. If you like to unmute yourself and ask a question.
Hi, Peter.
Hi.
I was wondering, how often do you do the checkpointing, and how do you decide about the frequency of the checkpointing? So how do you know?
I cannot give you a number of the checkpointing because that one depends on the memory constraints you have. We're using Revolve. That one is a library that is written by Griwank and Walter, and that one is doing binomial distributions of checkpoints. So it's pretty much automatic. It's a beautiful library that is doing the optimal job. You just give it the number of you give the memory requirements. So you say you have, for example, 5 gigabytes of storage, and each flow field is a certain number of gigabytes, and then it says, okay, I can afford 7 checkpoints. And then it distributes the checkpoints automatically for you. So they're not equispaced. There is actually some optimality distribution that you have. It's a binomial distribution along the time horizon. And then it writes out and injects it automatically when it needs it for the adjoint. So it's a really convenient library to use for checkpointing.
But surely there's a dependency on the nonlinearity, so on the solution, no? So it depends on the flow field, really. How often do you need these checkpointings to do the backward adjoint?
No, that's independent of the nonlinearity, because the checkpoints just are only taking into account the memory requirements. Once you have the checkpoints, you need to reintegrate the forward equation to fill in the flow fields that you need on the adjoint. So the distribution of the checkpoint has nothing to do with what you do with the checkpoints.
Okay.
So it's independent of whether you have U grad U or any other nasty nonlinearity. That one is independent. Yeah.
Okay, thank you.
Mm-hmm. Sure.
Vasilis.
Hey, Peter, brilliant talk. Thanks very much.
Thank you.
You took the Reynolds number at a value where there was no exponentially growing instability. You said that very clearly, because then all hell would break loose. My question is whether there is an algebraically growing instability, and if so, can you somehow correlate the linear optimal time with your time horizon in order to better perform?
Are you talking about the channel flow experiment or the one in the Petri dish?
Initially, I was thinking. I mean, the question came to mind in the channel, but perhaps there is a correlation in the.
Yeah, it's in the Petri dish. You know, it's hard to tell whether there is an exponential or an algebraic instability or something like that. But in the channel, it's a little bit clearer. That one was at a Reynolds number where there was no exponential instability, but there was an algebraic instability, a transient growth. And yes, the time horizon after that one, when you only give yourself 20 time units to do something, that very much depends on what the time scale of that transient growth is, how much you can actually squeeze out. Absolutely.
Thank you. Great.
If you do too short, there is not much you can squeeze out of a transient instability. If it's long enough, it may be part of your strategy. At least it's there to.
If your G is large enough, right? So
exactly, if the T is large enough, then the transient growth is at least there to exploit. Whether the optimization will use it or not, that's a different question. But at least it's a possibility.
Great, thanks very much.
Mm-hmm.
If there is no more question, we might close this session because I guess people trying to join another seminar organized by math department.
Oh yeah, there's the competition. Yeah.
We collaborate, Peter.
Good. Good. Glad to hear that.
Thank you very much, Peter. It's a beautiful seminar.
Yeah. Thanks for the invitation. Yeah.
Very interesting. Very complex.
Yeah, it is a little bit, but you need good students.
Thank you again.
Sure. Okay. Take care. Yeah. Bye-bye.
Again, thanks everyone for joining.
Thanks.
See you next week.